Good afternoon. We continue with our series on Six Sigma. The topic today is going to be statistical process control. There will be 4 lectures. The first 3 would focus on the use of control charts, the development of control charts, which turn out to be a very key tool to try to get consistency in production and also keeping up with quality. Once you have set up your machine and got the process to work right, how do you keep it there? SPC turns out to be the technique to be used there. The fourth lecture in this sequence of statistical process control will discuss process capability, which I'll follow after the first 3 sessions are over. So we begin our lecture with our title slide here, which says statistical monitoring of processes to detect special causes of variation. And as I go into the lecture, it will become more and more clear why we are talking about different types of causes of variation. You know, something that is very, very important for business to understand, for manufacturers to understand, for service providers to understand, and also for customers to understand is nothing stays the same when time changes. With time, a lot of factors change, quality changes, variations occur. A lot of factors come and go and they impact the process, and therefore we end up with some variation. But obviously with any product, if there is a lot of variation, the user will not be able to live with that. The customer is not going to be able to live with that. So for that we need some sort of control device. And control, the very word control always means there is a feedback mechanism. It looks at the results of the output. It looks at some summary of the output, which gives an indication of the nominal level of quality. That uses that feedback to compare it to some sort of standard. And if the deviation from the standard is too large, then of course you trigger a control action. This is the approach, this is the philosophy of any kind of control. In the case of statistical process control, what we do is we let this control be activated when the data shows an exceptional behavior. Then we go out and we sort of apply some fairly simple statistical methods to get a signal out of the collective data and then decide based on that collection whether or not we need to adjust something on the machine that's producing the widgets or do something about the process, or to just leave it alone. Any of those decisions would be impacted by a trace of the output, and this trace is actually a statistical trace of the output. This is what we study when we talk about control charts. Control charts are the devices that make the behavior of the process visible to us. As it is running along, as time is flowing by, how is the process changing in terms of its output? Something that is of interest to us, the manufacturer, and also to the users, the consumers. The outline of the lecture will discuss some basics. Then we'll discuss exactly the various things about the control chart, this key tool that is used in statistical process control. 2 types of charts are fairly common. One chart that is attributed to some quality that you can basically call good or bad. For example, a pen may be able to write or may not be able to write. So it's good or bad. Or this fit here may be a good fit or it may be a poor fit. So this is something where I can really categorize products to be either good or defective. Such quality performance, such quality characteristics, these are monitored using what we call the attribute control charts. Then we've got other types of quality characteristics where I can make a measurement. For example, the dimension, the length of this pen, or some dimension of the roundness of the tip, for example, those can be measured. And again, those measurements can lead to a set of control charts which are called variables control chart. You might have heard of the charts called X bar chart and range chart, R charts, and so on. Those come under the what we call variables control charts. And charts that are like the P chart and the C chart and the U chart and so on, those come in the category of attribute charts. Then we shall be looking at what we call some exceptional patterns that basically signal whether or not I need to take some action. So look at some of these patterns, some of the common patterns that appear in the chart, and these are the triggers. These are the triggers. When these exceptional patterns appear, these indicate that something has changed in the process. And if the process change appears to be significant, we will take some control action through a reaction plan. That also I'm going to describe to you as we go along. Then of course I'll give you some hint as to how you can set up this control chart preparation procedure using this common tool called Excel. I'll give you some examples there. And last of all, which will be done in the last session, which is the fourth session in this sequence, that will cover process capability. So let's get into the lecture and let's try to understand what we mean by statistical process control, which is also called SPC. What is SPC? It actually monitors the production process online. As the widgets or as the output is coming out, you measure some certain characteristics of interest of the output. Then you collect some data, which would be a sample taken out of the output, and then you look at the statistic, which could be something like X bar or P or R or something like that, and you trace basically the variation of that statistic. It could be X bar, it could be P, it could be C, it could be any of these characteristics. You monitor that as it moves along, and that's when you plot a chart, and I'll show you some examples. You'll actually see this trace taking place. As more and more data are collected from the production line, you'll end up with the chart moving forward. In the old days, the only way to control quality was that by inspection, and the statistical process, the statistical procedure which we covered in the earlier sessions, one of those was called acceptance sampling. You basically collect from a handful of items, you collect a few samples, and based on the fate of those samples, based on the quality of these samples, you'll decide whether to accept the lot or to reject the lot. That particular procedure was called acceptance sampling. That was one way to apply statistical methods in quality assurance. And this online control business, this comes under statistical process control or SPC. This is like this second class of applications of statistical methods in monitoring quality, in assuring quality. The third method, which is perhaps the most powerful method, that also is basically utilized by Six Sigma, is design of experiments. And I'm going to be spending some special sessions on that. So you'll get to know what DOE is, what design of experiments is, and how we can utilize that to produce better processes and also better designs that we'll be doing. So there are basically three opportunities for applying statistical methods in assuring quality. The first is, of course, acceptance sampling. The second one is SPC. And the third one turns out to be DOE or design of experiments. Today, we are going to be focusing on SPC. Statistical quality assurance, what exactly do we mean by this? We are trying to assure quality. So, trying to be proactive. Basically, what we are going to be doing when we do online monitoring would be monitoring the data online. That means as soon as a widget is produced, we make some measurements on it, we assess its quality. And we take a sample of these. We just do not always go with one item at a time. We don't do that. We will collect a few samples, and these samples will be collected. Then from that, a statistic will be calculated, which is a summary of the data that is coming out of these samples. That summary is what we plot on a chart. That is what we plot on a chart, and it leads to what we call statistical process control. The other methods, as I already mentioned to you, one of which is used after production generally. This is the acceptance sampling method. Acceptance sampling method happens to be one of the methods for this. And like I said to you earlier, we will be using SPC. We'll be studying SPC, and SPC is a method that is applied during production. What exactly is this? It's a simple method. It's a very powerful method at the same time. Once you understand what is going on, it's not very difficult to plot charts and to get signals out of it. And the signals basically tell us whether to adjust the machine or to leave it alone, because it's doing all right. There still will be some variations, but those are within the tolerance that the customer is willing to live with. Therefore, we leave them alone. But if there are wide variations, if there are large variations, then of course, it's a matter of concern, because when there are wide variations in the process, it's very possible that some of the items that get to the extreme values, those may go out of specification, and those may not be fit for use. And that's why we want to make sure we monitor the process as it is going on, as it is conducting itself, and then look at signals, look out for signals. Once the signal is there that there is something exceptional that is happening in the process, because some tool broke down or something happened, or a different procedure was used or something like that, or an untrained person came along and he started running the machine, and it produce parts that actually need to be basically production of such parts need to be minimized. That is when we would be going into plotting a chart, getting a signal out of it, and taking exceptional actions. What does a chart look like? I have a little plot here. Notice here there is a trace of these statistics. So if this was, for example, I'm jumping the gun a little bit. Let's say I plotted X bar, and I'll show you in a minute what X bar is. I plot X bar, and time is this way, time is on X axis, and X bar I plotted on the Y axis. There will be some variation, that is what we call the natural variation of the process. That much variation will stay there regardless of what you do, unless you tighten up everything. And if you remember the fishbone diagram that we had in one of the earlier lectures, there is almost no process that is not affected by something that is around it. So in fact, most processes end up with some variation. If these variations stay within some tolerance, we have no problem. We probably live with it. For example, when you go to a bank and you put down your signature on a check, if the teller knows you probably, and if you sign in front of her, there is no problem there. She'll accept and she'll give you the payment for that check. But suppose she receives this check in the mail and it claims to have your signature. She will compare your signature as it appears on the check against something that's a standard, that's an electronic facsimile of your signature that's already in their database. And she will compare the two. If the variation from the standard and your signature on your check, if this variation is small, she will say the two are probably the same, and I need not really worry about anything. This check is a genuine check and the signature is genuine. But suppose there turns out to be a wide difference between your signature as it exists in the records there and what appears on the check. If there's a wide variation between them, she will raise an alarm. And in the extreme case, she may refuse to make the payment. When she raises an alarm, she could do further investigation, perhaps make you a phone call or something like that. And if she thinks it's been a forged signature, it's a forged signature that is on that check there, she'll obviously not make the payment, and someone up there in the bank upstairs, he would be notified about it and you would be contacted. If this is not done, of course, our life will be miserable, because a lot of exceptions they would get in as if they are routine, and that's not going to be such a good news. We apply the same principle when we do statistical monitoring. So if you go back here, you'll notice that the chart that I have, the figure that I have here, I have a chart here, and the chart has two quantities. I've got the upper control limit UCL, and I've got the lower control limit called LCL. These control limits basically show the limits of natural variation of the process. So these are the different signatures I've done on variety of checks that I've written. If they are within this tolerance band, there is no real problem either for the teller or for the bank to make a payment to me. But suppose my signature lands up here somewhere, or my signature lands up here somewhere, that actually is a wide variation. It's a significant variation from what that norm is, the normal signature. Here, of course, I'm not dealing with signatures, I'm dealing with product quality. And product quality has been measured and has been converted into a statistic such as X bar or R or P or C or C. And these are the ones that I monitor by plotting them on the chart. And for each of these quantities, X bar, R, P or U or C or any of them, these are indications of quality. There are going to be control limits. So one of our jobs is going to be, for the selected statistic, we must also come up with these correct control limits. That's going to be an important. Now, what all things do I need? I need a couple of things. I need a sample. I have production going. I have full production going smoothly. But once in a while, I'd like to check the quality of it. Is the average quality being maintained the way the target was set? Is it being maintained, or is it a deviation from it? Is the process drifting upward or downward? Or is it going away and then coming back again? Such things are really not very desirable when you're assuring quality, when you're running a production system. Such variations are, sometimes they are not acceptable. Certainly they are not going to be acceptable to a customer who sees a lot of inconsistency in the output. So this is something we would like to be able to avoid. What do we do here? We plot a chart and we compare the data to these control limits. The data I got was from this sample. And a sample actually basically is a representation of production that is going on. The real production may produce thousands of these pens per day or perhaps even per hour. And perhaps every 15 minutes, I walk up to the machine, I collect a handful of those pens, they become my sample. These are the ones that I inspect 100%. I check out the quality of each of them and I compute this quantity called X bar from the sample data that I have. And X bar is what I bring down to my chart now, and I plot my X bar, and by plotting that X bar, I basically reach a decision whether I need to adjust the process or can I leave it alone. This device is called the control chart, and the goal of this chart is to try to help us keep the process within control limits or within its natural variation. For doing any of these things, you need to do some measurement, and it goes without saying that your tools must be good, your instruments must be good. If you're going to be using these for plotting control charts, you better make sure that the data collected are correct, and of course the calculations are also correct. To make sure that the data collected are correct, you got to make sure you've done your gauge R&R, gauge reproducibility and repeatability study you've done. So you've made sure that these instruments which I'm going to be using here, these are the instruments that, by the way, they measure dimensions. You got to make sure they've been calibrated, and also we know exactly if they have any drift or anything like that. So gauge R&R, which is the variability that is introduced by using the gauge as a measuring device, as something to produce data, that is behaving all right. That has its own variation, own contribution to variation to the ultimate data, kept within a very tight tolerance. If I plot raw data, my data stream is going to be looking like this. Look at the variation. This is just the plot of raw data. So if I produced a lot of these, pens, and I made a measurement of the dimension, for example. There are certain things that are critical in manufacturing a pen, and it could be the dimension. The dimension has to be within some limits, within some specifications. Suppose I just take pen after pen and I write down the dimension. Length is 1, then length is L1, then L2, then L3, and so on and so forth. And I basically take that set of raw data and I plot them. If I plot them, I get a trace just like this trace here. I get some variation. Now these variations are there because if you recall your fishbone diagram, there are many factors that can impact the production of these pens. Now many of these factors are such that their own individual contribution to this variation is small. But there are many such factors in place. While production is running, I've got many such factors impacting the thing, and therefore there is going to be their combined compound effect. That's why you see a lot of variation when you see a chart like this. But this is a raw chart. Is this raw chart good enough? The only thing I can do, if I've got only one piece of data, in my hand, which is the raw measurement taken on one item, the only thing I can do is to try to check and see whether it meets specifications. That's all. There are other things that I'd like to know about the process. I'd like to know about the behavior of the process. And the two key ones are, is the process running accurately? That means, is the average production quality pretty close to my target? That's like the indication of accuracy. The other thing is I'd also like the production to be, I'd like my process to be precise. That means whatever these variations are, they should be within a tight tolerance. Both of those things are important, certainly for the user. The final user who's going to be using these outputs that I produce out of a process, those got to be accurate and also they got to be precise. So the output has to be precise and also it's got to be accurate. I cannot do this. I cannot really control these two aspects of quality, which is accuracy and precision, just by using the raw chart. I cannot do that. It's not possible. I have to convert this raw data into something else, and I'll show you exactly what I do. In fact, this is the heart of statistical process control. Now look at a process. I've got a process here on the screen, and the process started here. Notice here process mean was mu0, and some specification limits were put down here, lower spec limit and upper spec limit. and the natural variation, the process kept all the data within this thing. And this is what we call the process. When we say that the process is under the influence of chance causes only. Chance causes are exactly those things that let your signature vary a little bit from check to check to check. Those small variations, they are due to chance causes. You don't really hold the pen exactly the same way every time you do your signature. Your speed may change, your strokes may change a little bit, but they are all within this tolerance. They are all within this small tolerance. And this small tolerance basically reflects the natural variability of my signature. And the same thing here for quality. This bell curve here, look at the bell curve on the left, the starting one, it shows the natural variation. This range is the natural variation of the process. But as time goes along, once in a while I find that the whole process has shifted out. It ran all right up to this point. Then I find that my process shifted to the right. That means the new mean mu1 is greater than the original mean, which is mu0. It's shifted out to the right. Now this actually causes, this impacts the accuracy of the process because the mean has changed. So it will impact the accuracy of the process. It's also possible that your accuracy is fine. Like for example, look at this one, this third curve here. Accuracy is fine because the average is still at mu0. But the problem is the process has become wider. It's taken over a wider distribution. This is when precision has got affected. It's become wider. And that would mean there is a chance, of course, that toward the tail end of this output, this population output, I may have some parts which are not going to be fit for subsequent use. So we have two problems here, as you noticed. One is the issue of accuracy. That means is the process average staying on target. And the second thing that we have is the process precise. It's holding on to consistency. That means whatever sigma was there in the process to begin with. When I started out, I set up the process and I turned our system on and started to produce my widgets. Is it staying with the same precision or is precision getting worse? Generally speaking, we get concerned when precision becomes worse. You see that when you see this path here, there is accuracy changing once in a while and also there is precision changing once in a while. Both of these could be problems. Both of these situations, which is a shift in accuracy, could be a problem, and also a shift in precision could be a problem. So we got to do something about them. Let's try to again recall this diagram, which some of you might have seen earlier. I have four people who are trying to shoot their gun at the targets which are here. Now there is one person who is totally untrained. He's been given a gun and he's been asked to fire, and he fires a few shots. The distribution of those shots, they are shown here. The target is right there, bullseye is right there, and these indicate the positions of where the bullets went by. So you have this variation here. There are two problems with this sort of performance. One is, look at the average of the distribution of these little holes there, bullet holes. The average itself is of the what we call the bullseye. So there is a problem with accuracy. Also notice this spread is rather wide. This spread is rather wide. So I'll say precision is also poor. There is poor accuracy and also there is poor performance in terms of precision as far as this shooter is concerned. Look at this shooter now. This shooter has his average right on the bullseye. So therefore accuracy is not a problem for him. And I show that in green, letter A, which indicates accuracy, it's green. That means we have accuracy and control there. But precision is poor again. Look at the wide spread. Look at the third shooter here, who's got his distribution of the different shots pretty tight. So precision is there, but unfortunately, the average is off target, so it lacks accuracy. And look at this fourth guy, who shot all his shots very close to each other, and the average is right on target. This is what we would like to be. We would like to be not here, not here, not here, but right there. This is what our process should be like. If you have a process going like this, the parts that come out of a machine that is doing the performance 4 type of performance, these parts are all going to be fitting well. So no matter what cap you pick and what body you pick, if these are both accurate and precise, they are all going to fit. This is something that we'd really like to have anytime we've got mass production. We'd like to have accuracy and also precision in the manufacturing of our parts. Let's see now what our task then becomes. We have a running process, and the running process, as I showed you, the raw process may have all kinds of variations. But what we should be concerned about is the process accurate? Is it producing on the average, is it producing output that is staying right on target, number one. Number two, is the process also performing in a precise manner? That means, are the different pieces of output, are they close to each other? That is also something that we'd like to be able to do. If I do not control these things, and if I just look at the output of a process which is not being controlled either for accuracy or for precision, we'll end up with performance that looks like this. Now, before I show exactly what is going on here, let me show you the quality characteristic is plotted on the x-axis. The quality characteristic is plotted on the x-axis. Now, there is a limit here which is called the upper spec limit for the parts. And this is the upper spec limit, which actually says if I produce parts which have dimensions which are beyond this upper spec limit, those parts are going to be useless for application. So, in fact, if I was producing these caps, and these caps were produced with two wide holes, again those would be useless to be used in the assembly of pens. In fact, it might turn out that those caps, those would end up being in the off-spec area, either to the left, which is like the caps are too tight, or they might be too loose, which is to this side. Both of these are harmful. One reason is this: it costs me the same whether I produce a part that is within specification or outside specification. The machining process itself does not change the cost of production from item to item to item. It does more or less the same thing as the different pieces are floating through the thing. But if I end up with a lot of products which turn out in the lot of parts which turn out in the red area, either off spec because it's too tight, or it is too loose, therefore it is again off spec. It turns out both of these, if these are large share of our production, we've lost that much money because we cannot sell these parts, we cannot use those parts. The only parts that we can use are those that are within specification. So what would you like to do is, first of all, we'd like to have the output average exactly on target, and not neither to the left nor to the right. So I show the target here with a green arrow there. The process average should ideally be exactly right there. That's like something we'd like to be able to do. Now that's the midpoint of the specification range. The second thing that we'd also like to do is, would not like to see as much variation as is shown on this graph. Rather, we should have a sigma. We should have a sigma that is fairly tight and stays pretty close to the that midpoint there. So that way we'll be getting accurate production and also we'll be getting precise production. The role of control charts is to try to help us remove all those factors that might either impact accuracy or it might impact the precision of the process, to make sure what we produce can be sold without any problem at all. Or those could be used in your subsequent processes. Where do these variations come from? They come from a variety of different causes. Causes which are large in number, but they individually produce very little impact. It's like the manner in which you hold your pen, for example, when you're doing a signature. Every time I pick up the pen and I hold it, there may be some slight variation in my holding the thing. That might affect the quality of the signature. It might affect the quality of the signature. Those are called chance causes, and those are also called random causes. These causes are inherent in the process. That's part of my biology. The way I hold the pen is part of my biology. And these may be eliminated only through improvement of the system. So if I take some training, for example, children when they are small, when they are just trying to write, they are learning to write, they are told how to hold the pen. You know, you have to put it like this, you have to rest the thumb against it, you got to rest this index finger there and the mid finger should be somewhere else. They got to hold it like this, the angle should be like that and so on. If you don't teach it, many times children, they tend to hold a pen like this, or they may hold it like this, and they may hold it in various different ways. If you hold it in any manner, that's not the standard writing manner. There will be more variation in writing, and your handwriting is not going to be in your control. There will be a lot of variation. those are holding the pen like this, or like in some manner that's not the standard method, for example. Those are what we call non-random causes of a variation in your signature. The same thing we have in production also. When we produce these widgets, these items or these parts, there are these special factors, and I'll give you many examples of these as we go along. These may cause large variations in the system, large variations in the output. And these factors, these outputs are generally, these factors can generally be identified. For example, if you see a crazy signature, you might actually ask the person to do a signature again. And if you find for some reason, maybe he's got a cut in his finger and he's got a band-aid on it and it's paining, that finger is paining, he's not going to be able to rest it the way he would normally do. He'd probably make some exception. He might buckle his finger or something like that, and he will just put his signature like that. That's an exception. And this would impact the output, this would impact the quality of the signature itself. And this is something, naturally, if it is going to be used, if it's a signature for a check, this is an exceptional situation, and people have to be notified about it. And in general, if this happens in production, you do not want to continue doing production when you got a situation like this. You've got one or two of these exceptional factors impacting production that you should not be forced to do. And these special causes of variations are the ones that we detect by using the control chart, which we'll be seeing in a few minutes. So again, to summarize, there are these common causes. Those cause small vibrations, small variations, and they are many in number, they are large in number, but they don't really have a big impact on quality. They don't really have a big impact. But then there are these assignable causes. These are the special factors, such as I have a cut on my finger and I'm trying to write with the pen and I'm not able to get a good signature. That's going to be the exceptional case. And in production also, if the tool has broken, or if the cooling fluid has stopped for some reason, or there is some other problem with the machine itself, it may not be something I'd like to carry on with. And this is something we'd like to be able to avoid. And again, the control chart is the way to do it. How do we actually use control charts? We take periodic samples. We plot the sample points on the control chart. We determine if the plotted points are within what we call control limits. These are different from specification limits. Specification limits are used to evaluate each single item, whereas control limits are used to look at the statistic, the summary of the data, which could be the sum total averaged out of measurements that are made on a number of different parts. For example, in this case, it could be the X bar, or it could be the range, the R, which is what I calculate using the raw data there. And that's the one that I plot. Those are the ones that I plot on a chart. And I try to see if the plotted X bar value or the R value is within what we call control limits. If we do that, we'd be preventing a lot of quality problems. So again, let's take a look at it. We saw the plot of the raw data. The same data was converted into X bar, and I'm going to be showing you how to do that. You have a collection of raw data, which are like individual measurements on these pens, dimensions of these pens, and you do a simple calculation. You calculate the quantity X bar from the X values. So you've got X1, X2, X3, X4, X5. These are 5 individual data points. You'll calculate X bar, and as the name implies, X bar is the average of those Xi values. This is like one statistic. I calculate a similar statistic called the range, which looks at the highest value in the data collected and the smallest value in the data collected within that sample. The difference between the highest value and the lowest value is what we call the range of the data, of the variation. This range actually is an indication of the consistency of the process. If the process is very consistent, the range is going to shrink down to pretty close to 0. But if the process has a lot of variation, range is going to expand. In some sense, this range is similar to what we call standard deviation, and we'll see that as we go into this theory here. This is now a plot of the standard deviation. The same data that you saw earlier, the same raw data. First we constructed the X bar statistic. Then we also calculated the standard deviation statistic. And let's just recall for a minute what these formulas are, and I'll be using this little piece of paper here to be able to do that. Let's say I collected some raw data and I looked at 5 pieces of parts that were produced. These are the 5 pieces of individual data points that I collected, and these are what? They are measurements. They are measurements done on these individual parts. So I had one measurement done for the first one, second one, third one, fourth one, and fifth one. I've got 5 pieces of raw data. What is x bar? Let's try to write the quantity for x bar. X bar is a very simple formula, x bar, which is also written sometimes as x bar. It's basically the average of this. So this goes as x1 plus x2 plus x3 plus x4 plus x5 divided by sample size, which is 5. This can also be written as sigma xi divided by n, when n is your group size, subgroup size. This is one statistic which I can plot, and I showed you that plot of x bar. That was actually, let me just show you the x bar chart. This is the x bar chart. And notice here on the y-axis I've got something calling itself x bar, and on the horizontal side I've got sample number. So sample number could be sample 1, then sample 2, sample 3, and so on. For each sample I'm calculating an x bar value. Then the other quantity that I can also calculate is the standard deviation, and remember the formula for that. I'll just write it here as S equal to, and for this I need to do a little bit of calculation, not too bad. I'll do a square root first, then I'll do sum xi minus x bar square, and this is to be summed over the full sample I equal to 1 to n. That is all fine. Divide this by n minus 1 and take the square root of the whole thing. This is my standard deviation. This is my sample standard deviation. X bar would be utilized to get some sense of accuracy of the process. It basically indicates the central tendency of the process. Then we got something called standard deviation, which indicates basically the spread of the process. There is another quantity which is not as complicated to calculate, and that is called the range R. R is the same as range. And what is this? This is equal to max xi minus min xi. The largest value in the collection of the data there and the smallest value in the collection of the data there. So the difference between the largest quantity and the smallest quantity, this difference here is R. This is the range. And that is something that we'd like to get an idea of, because range indicates, again, like standard deviation, it indicates precision of the process. And we'll be looking at some real data. We'll actually see how these calculations are done. And to be able to do those calculations, of course, I brought my, the real precious computer, my little calculator. I'll be using the calculator every now and then to calculate the data points, various data points for the x bar quantity and also for the range quantity. That we'll be doing. Most of the time, I'll not have to use the standard deviation formula. One could do this, but it's a lot easier if I'm getting the same use of this or this when you're trying to do process control. Then why don't you use the simpler one, which is the range chart. So I have here, if you see the screen there, I have the standard deviation chart, and the very next chart is going to be the range chart. That also is shown. Control charts are therefore a key tool in SPC, and with this I can monitor the process graphically. I can do that by plotting the x bar chart or the range chart. Then there are some other charts also. For example, the weighted moving average chart, that also can be used, or the QSIM chart, this also can be used. These are other charts that have some special benefits, but they are more complicated. We'll be focusing today we'll be focusing on the x bar chart and the range chart. Then of course there are other charts called the P chart and the NP chart and the C chart, which we shall see as we go along. So what is a control chart? It's a time ordered plot. That's what this is. And it provides you with a signal when there is no special cause impacting the process. Nothing has gone wrong, nothing profound has happened to the process, and the process remains within what we call your in control, is a in control state. And of course, if some wild things happen in the process, like a tool breaks down, or the raw material is changed, or a new operator comes along and he starts operating the machine, those are likely to cause some exceptional variations in the process. And the process, the control chart may go then out of control. So I've got these two situations. I've got something called the process is in control, which is the base case, and the exceptional case is the process is out of control. These two I figured out by looking at the actual chart itself. So here is an example. I plotted the chart. So I've plotted here, for example, I might have plotted the x bar value. When I plotted the x bar value here, and I've got the plotting done for various samples that have come along, I notice the upper and lower control limits. These control limits have been marked, and I'll show you the formulas for these. There are some special formulas that are utilized to control the to calculate the upper limit and the lower control limit. Once these are known, I can plot the chart, I can plot the data. These are going to be x bar values, and I can check to see whether any point plotted has gone beyond the control limit, either beyond the upper control limit or below the lower control limit. If that happens, that's an indication that perhaps this variation has been caused by something exceptional. Perhaps the teller has to then look at the person and figure out, oh, he's got a cut finger, that's why probably his signature is bad. If not, she might just say, I have a suspicion that somebody has tried to forge your signature. Would you please verify this? Because suppose she treats this as normal variation, it is possible that some fraud had come along and it forged the signature. It's very possible. You want to prevent such things. You want to do the same thing in a manufacturing situation. When there's production going on to produce hundreds and thousands of these parts, you don't want these parts to be produced such that they actually violate the specification limits or they are unfit for the user's use. These are not going to be good news. These are not going to be good news for anyone. So you plot the chart and we try to see, are there any points that have gone beyond the control limits? If they have, we have to stop the process, do some investigation. Now notice here, I did not plot x. When I plotted the control chart, I plotted something called x bar. And the distribution of x bar turns out to be narrower. Why is the distribution of the x bar chart narrower? Let me just show you, just by showing you what happens when I go back to the formula that I wrote here. Notice the x bar, the formula for x bar is, I have sigma xi divided by n. If I try to write down this quantity, sigma x bar is actually the standard deviation of this quantity x bar. Now these x's are random variables, therefore this is also a random variable. And this will also have its own mean, its own standard deviation. It turns out the standard deviation of x bar, it turns out to be the standard deviation of x divided by square root n, when n is sample size. So the larger is n, the narrower is going to be this, the tighter is going to be my sigma x bar. And that's why you notice here, when I go back to my, when I go back to the screen there, the curve on the left, the bell curve on the left, this wide one has a larger sigma and this guy has a smaller sigma, because this sigma is going to be sigma x divided by square root n. That's what this thing is. That's why control limits are always narrower. Control limits actually have nothing to do with specification limits. Control limits are calculated based on the data. The data that you have, and some constants are there, some multipliers are there. But basically control limits are calculated using the data that you've collected when the process is in control, when there are no wide variations there. That we'll see again when we get into the calculation of control charts, the control limits. So the process basically is in control if there are no sample points that are outside the control limits. Most points are near the process average. This is also a good indication that the process is in control. That means it's under the influence of random causes or chance causes only, and none of these exceptional assignable causes, the ones that really create trouble. About equal number of points should be above or below the chart. If that is there, above below the central line of the chart, that actually says that the process is stable and it's staying pretty close to where it should be. Points appear to be randomly distributed. There is no like biasing toward the upper side of the chart there or the lower side of the chart there. That sort of pattern is not there. In fact, it does appear to be completely random. Then of course, the process is likely to be in control. And of course, we say that a process is in control when it's under the influence of random causes only. Look at one chart that is shown here, and it's very possible that this chart till this point the chart was in good process control, and something exceptional happened that bumped this thing, that bumped the chart, bumped the X bar value, and it went beyond the control limit. It's very, very possible when you investigate this chart, when you go back and investigate the process, you will find a broken tool or a stopped hydraulic line or something, or maybe a new person came along and started fiddling with the machine, or raw material changed, or voltage fluctuated, therefore the cutting speed changed or something like that. When those things happen, of course, you'd see charts going beyond the control limits, and you end up with exceptional situations like this. At this stage, you are supposed to investigate the process, and you are supposed to remove that cause of variation, the cause of extra variation, and you are supposed to then resume your normal production. What are the various things that can lead to process variation? There are a number of them, and these have been broadly classified through history as factors that can be traced down to operators. For example, their training, the quality of their training, the kind of supervision they are receiving, the techniques that they have been taught, that they have learned. If there are variations there, this would end up showing up on the control chart, because operators are a key part in that total production system. Then of course, the method itself, what are the procedures? Are they following the standard operating procedures? What is the setup like? Does it change from setup to setup? What about temperature, cutting speeds, and so on? These are all parts and parcel of the method itself. These may also lead to light variations in the process. Then of course, raw material, I don't have to tell you that when that thing changes, again quality will change. And the machine, that also can be there, and the management process, poor process management, that can also lead to a lot of variation. And here's like another way to present the same thing. I've got the same thing. If you recognize the tool, it is the fishbone or the cause and effect diagram. And quality variations would be there when there is lack of maintenance, faulty specifications, the vendor has some problems there, or the sheet metal that is being used, it's got some problem there. Personnel might be also causing variation because the incentives are not good enough, lack of training is there, and the procedure is there, but there is no documentation. So each person, he uses the procedure in accordance to his own understanding. These are the variety of different factors that can lead to the chart fluctuating. If you had a lot of money, you'd remove all of these factors, but generally speaking, we don't have that. So what we have to do is, it's like if you just wanted to get a taxi and you wanted the president to ride in that taxi. Of course, the president will ride in a limo. The driver that you're going to pick for that limo, that driver has got to be an exceptional driver, because he should not have any kind of problems in regard to his performance as a driver. What if it's like an ordinary person, who does his probably own driving, or probably, his demands are minimal? Then with moderate training, perhaps he drives only a tractor. He could also drive a car, and his performance obviously is going to be highly variable. So with training, you can improve. With training, you can improve. With a lot of other interventions, you can improve a process. And slowly, as you spend money, the variation in the output is going to get narrowed down. And we'll see that as we go into some of these examples. We'll see how it started with a wide variation, then it became somewhat tighter, and it converged eventually to exactly what the customer wanted the output to be. But it would cost you money and time to come down from this end to this end to this end to this end. It would cost you time and money. If you do it the right way, using, for example, design of experiments, this march can be pretty quick. And if you just count on trial and error, you'll probably get there, but it will take a long time. If you have a good trainer, if you have someone who is knowledgeable about the process, he can probably let you reach that end point pretty quickly. Charts may also, of course, signal incorrectly. It's very possible because these are all random variables. So it's very possible when you see a point which is beyond the control limits, there really were no assignable causes that lifted it up there. It could be a few random causes that combined together, then they produce that big jump there. So it's very possible that charts once in a while may give you a wrong signal. We should be ready for it. We should be able to tolerate if you're expecting to produce output that is going to be satisfactory for the user, we might be a little conservative. There is no harm there. The result is going to be always better. It's always going to be good. Let's take our time. Let's make sure we understand the process. Let's make sure we install the control chart system there, and we'll do some design work there that like we'll calculate the control limits and so on. We should not make any mistakes there. If you make a mistake there, of course the chart will give wrong signals. We should not do that. But once you have things in place, then there's going to be no real problem at all monitoring this process day in and day out. You'll get the same performance, same output. Do stay open to some of these errors with the control chart. That means the chart shows that it has gone out of control, and you end up doing some unnecessary troubleshooting as a result of that. Please tolerate that, because you are trying to be conservative. Even if there is the slightest chance of an assignable cause that might have come there, you don't want to miss that chance. You don't want to miss that chance, catching that chance sort of. So you better make sure that you've got lots and lots of extra time to do your investigation. You might be doing a bit of witch hunting once in a while. That means the process is fine, but the chart gave a wrong signal because of the random combination of things. It's also possible, of course, that the process itself has become worse. It has become bad. But even if it is bad, it turns out that the chart is within your control limits. That's also a wrong signal. In fact, you're not getting the signal when you should be getting a signal. So let's try to see what we could do. We have attributes. Attributes, as you understand, they are quality characteristics that I can categorize between good and bad, and I can draw control charts based on these, and those would be the P chart and the NP chart and the C chart and the U chart for attribute characteristics. Then I could have something that we call variables characteristics, such as dimensions, for example. Those are measured, and then you convert those measurements into either the X bar or the R chart. In fact, you do both, and then you plot the X bar chart or the R chart on a control chart paper, and you try to see are there signals there. Variables, examples of variables characteristics, are a lot of examples given here. Length, weight, time, volume, temperature, and so on. These are all quantities that I can measure. Attributes, on the other hand, are good and bad, and thus, like, is the pen able to write or is it not able to write? It's just sorted between good and bad and so on. So that's an attribute that can only be monitored using what we call the P chart or the NP chart or the C chart or the U chart. So these are the ones that lead to these various types of charts that we see. We see the X bar chart and the R chart. These are the most popular chart. Then you got the P chart, which is also pretty close to the X bar and R chart in terms of popularity. Then you've got the C chart, and we'll see that we make this choice based on whether the characteristic is variable or it is an attribute. And of course, in some exceptional cases, you might like to use the QSUM chart, which has got some extra power, or the weighted moving average chart. That also exponentially weighted moving average chart. Those also we may use once in a while. And of course, I was only talking about dimension, which is only one characteristic. It's also very possible I may have multiple characteristics that I start plotting on a chart, not on a single chart, but there are special charts which are like multi-attribute charts, and these are multivariate charts. They also give signals just like this, and they also have something called control limits and so on and so forth. We'll see them. We'll see a couple of examples of these as we go along. What does a chart really do? It lets you test this hypothesis. What is your hypothesis? The first hypothesis is the process is in control. The test of the hypothesis, plot that point. The moment you plotted that point and it has turned out to be that it has gone beyond the control limit, you say to yourself, I cannot hold on to the hypothesis that the process is in control. The process, I must abandon this, and I must investigate the process to say that process is out of control. Can I find the root cause? Can I find the reason why it is out of control? And the same thing can be done for services also. We talked about manufacturing, we talked about pen production and so on and so forth. We can do the same thing with services also. And I'll continue with this as we go into this session here, the next session. We'll be looking at some of these service examples. Thank you.